Okay, so this mini lecture is going to look at the concept of uniform circular motion. So what is uniform circular motion? Well, it's very well named. Uniform circular motion really just means an object moving in a circle at a constant speed. And I'm very careful to use the word speed. How come that might be? Why do I have to say it's moving, an object moving in a circle at a constant speed? Well, the other way that we describe how fast something is velocity. Why isn't an object moving in a circle going a constant velocity? Well, if it's moving in a circle, then it's changing direction. And velocity is worried about direction, and so it's not actually moving at a constant velocity, but it is moving at a constant speed. So let's think about that in terms of what that tells us about the motion and what must be happening. So if an object is moving in a circle at a constant speed, we're going to look at sort of the top-down view. Let's imagine you are spinning a ball on a string over your head, and it's moving in sort of a horizontal circle above your head on a string. If we look at the top-down view, that ball is moving in a circle, and your hand is holding onto the string. Let's say we take a snapshot of the ball moving in that circle when it's here off to the right. All right. As it moves around this circle, and if it's moving at a constant steady rate around that circle, we know it's changing direction. If it's changing direction, if there's a change in direction, even with a constant value, this implies a change in velocity. Well, a change in velocity means something very specific. This tells us that there's an acceleration. And if we have an acceleration, that tells us that there's a force. And indeed, a force, something is causing this object to move in a circle. And we want to talk about how that force looks, how that acceleration looks, and this whole package is what we refer to as uniform circular motion. All right, so let's think about that. Well, here we have our object moving around in a circle. The object we're interested in is this ball on a string. All right, so the object is the ball. Now, if we think just about the circular motion part, we're not going to worry about it moving in and out of the plane of the board here, or what forces may or may not be at play with its static motion in and out of the plane. But let's just think about what's causing the ball to go in the circle. Well, what's the ball interacting with? Well, it interacts with that string. So the string is causing the ball to go in the circle. So it is the source, the string is the source of the force. It's kind of hard to say. The string is the source of the force. The two interacting objects are the ball and the string. Now, we often think of a string as tension. So let's first think about what facilitates the magnitude of that force. Remember, forces have both magnitudes and directions. So let's talk first about the magnitude. What influences how strong, how much tension that string exerts? Well, we're going to have to think about, imagine some things. So what happens as I'm spinning around a string if I spin it faster? Faster, faster, and faster. Is it more difficult for me to hold that object in a circle, or easier for me to hold that object in a circle, to keep that object moving in a circle? The faster and faster it goes, it actually is more difficult to keep that object moving in a circle. So the magnitude of that force, how hard it is to move that object in a circle, is dependent on how fast it's moving, on the speed. So if I increase the speed, and we're going to use lowercase v for that, then I'm certainly going to increase the force necessary to keep that object moving in a circle. It turns out it's a big difference, a big deal. The force is actually proportional to the speed squared. So a small change in speed gives me a big change in the force needed to move that object in that circle at that particular circle. All right, well, what else is dependent influences the magnitude. In this example, I want you to think about driving around in the country. So you're driving around in the country and you're going 60 miles an hour. And you see a curve up ahead, especially in these beautiful Wisconsin roads, at your northern Wisconsin country roads. You see this nice, gentle curve ahead. So you take it at 60 miles an hour and you have to keep your car steady as you go around that nice, gentle curve. But then up ahead you see a really, really sharp curve. Now, to go around that really, really sharp curve at 60 miles an hour, that's different. That is going to take a bigger force to keep that car going around that curve as going that fast. It's harder to keep your car on that curve going 60 miles an hour. So what's different about those two situations? Well, the radius. The radius of that circle is different. The radius of that curve is different. As we increase the radius, so I make a larger curve, a more gradual curve, it doesn't take as much force to move that car around that curve. So as I increase the radius, I decrease the force necessary to move that car in the circle, to make that car move in a circle. And so the radius and the force are inversely proportional. Now I'm going to just represent that as sort of a proportional sign to the -1. So inversely proportional to the radius. Now, what else might affect the force necessary to move an object in a circle? Well, if we think about Newton's second law and the general idea of Newton's second law, mass was important. The mass of the object is also important in terms of how the force is utilized. And so, just like with all forces, if we increase the mass, we increase the force. And so if we put this whole package together, we find the relationship for the force that causes an object to go in a circle, at least the magnitude of that force. We'll talk about the direction in just a minute. So the magnitude of the force that causes the object to move in a circle, I'm going to put that as subscript C. We call this the centripetal force. We'll talk about that name in just a minute. The magnitude of that force is equal to the mass times the speed squared over the radius. So directly proportional to the speed squared and inversely proportional to the radius. Now, the reason I drew it this way or wrote it this way is it allows us to think about Newton's second law. Newton's second law tells us that the force in general, the sum of the forces, is equal to the mass times the acceleration. And the same is true when we're dealing with objects in uniform circular motion, moving in a circle. When we're dealing with objects moving in a circle, we see that the force is equal to the mass times an acceleration. This portion of our equation is what we call the centripetal acceleration. So this is the value, speed squared over the radius, of the acceleration that the object is experiencing as it moves through that circle. So it does follow the same relationship as Newton's second law. Now this centripetal force is the net force causing the object to move in a circle. In our example that we used to set it up, that net force was being caused by the force of the string. So the tension was equal to our centripetal force. We're going to find in examples that sometimes it's a combination, just like it is for any acceleration. It's the net force that's causing the object to move in a circle, and it might be a combination of things. So we want to keep in mind that this relationship really is just like Newton's second law and dealing with the net force. All right, so that's our magnitude, our amount, our strength, and those are the things that influence the strength of that force, and specifically the strength of the centripetal acceleration. What about the direction? Direction is always very important in any vector quantity, particularly in physics, and in forces they're certainly a vector quantity. So what about the direction of that force? Let's go back to our picture. Well, typically we think of directions as right and left, up and down, forward and backwards. So we've talked about those directions in a very specific way. We have to change the way we think about direction a little bit when we move into circular motion and the direction of that force, and apply that knowledge to then the physical world of rights and lefts. So what is the direction of this force? Well, this this is our top-down view of the ball being reeled around this on a string. If I have the ball and I freeze the ball when it's out here like this, what is the rope doing? Is it pulling the ball or is it pushing the ball? Well, if I feel that tension in the rope, I sort of feel a little tug on my hand, which means the rope is pulling a little bit. The rope is not pushing. That tension is not a pushing tension. That would be sort of weird to have a rope pushing on an object. It's sort of a pulling tension. The force, sorry about that, the force is in that direction. And that's all good and fine, but what if I froze the ball when it was at this location, sort of directly in front of me? Well, then the string's sort of pulling it this way, and if you think about you trying to pull that ball in a circle, you feel that pull inward. Well, then the force is in that direction. So it was in that direction, and now it's in that direction. And subsequently, if I freeze the ball at this location, again, this is our top-down view, so there's the ball on the string, well, the string is sort of pulling it in that direction. So it's similar to all of these. Well, the force is towards the center. So the direction of the force, regardless of where that object is along that circular path, the direction of the force is towards the center. It's always towards the center. In fact, its name tells us that. It's centripetal, center-seeking force. That even reminds us that that force is always directed towards the center. Now, if we're looking at the net force of a whole bunch of things, towards the center might mean something physically different in different situations. In this example, when the ball stopped here, towards the center is to the left. In this example, towards the center is down. In this example, if I were to look at the force, when the ball is at the bottom, well, that towards the center is up. So when we identify the directions of the forces, we have to pay attention to that in terms of our traditional identifying of directions. When we think about what the centripetal force is, it's always towards the center of the circle. All right, so that's centripetal force. Magnitude is dependent on the speed squared and the radius, and the direction of that force is always towards the center. And it's just like all of Newton's second law forces. All forces within Newton's second law, it's the sum of the forces that cause that circular motion. Not any one, unless, like in this example, there is only one force. Now, this word sounds awful familiar to another word that I want to bring to your attention. This is the word of centrifugal or centrifugal force. So what is that all about? If we think about a centrifugal force, it's a feeling force. It's actually a fictitious force. It doesn't really exist, but it certainly is something that we feel or that we think we observe. Imagine if you were spinning that ball on a string, or if you yourself was on one of those really nauseating chair rides at the amusement park. You feel yourself being pushed to the outside, fully to the outside. The ball, as it goes faster and faster and faster, it gets pushed to the outside. A pizza dough, when the pizza guy is spinning it, what's happening? That dough is getting pushed to the outside and then spreading out, and we can have our pizza. Why are these things moving towards the outside? Is a force pushing them towards the outside? No, it's really not. Actually, what's happening is just a product of Newton's first law. So let's imagine this ball on the string again. I'm just going to erase these other images so that we can not be confused by them. So we have this ball on the string and it's spinning around in this direction. Spinning and spinning and spinning. Let's say at this very instant, the string is cut. What does the ball do? Well, what we need to do is look at now what happens under the case of the force being removed. The ball was moving in the circle because we had a force. Well, now as soon as I cut that string, I no longer have a force. There is no longer a net force. Well, what does Newton's first law tell us? It tells us that in the absence of a net force, objects continue moving in the fashion that they were, whether that's moving at a constant velocity in a straight line or whether it's staying still. So what is the object doing right at the point that the force is released? Well, the velocity of the object at this point in time is actually straight up on my picture. Remember, this is a top-down view. And what the force does is it changes the direction of that velocity. It pulls the acceleration is towards the center. So it turns it. If I take that force out, in the absence of that force, the object will simply do what it was doing right when that force was removed, which is heading in that direction. And the ball will go flying outward, when in reality, it's straight ahead or straight from the circle that it was on. So there's nothing that we feel, there's nothing that we are interacting with. There's nothing interacting with the ball to make it go straight. It's the absence, the taking away of the force that makes it go straight. I'm just going to throw in one little fun, quirky neuroscience thing because I love neuroscience. And it's hard to convince me, you, a 5-year-old kid, that they don't truly feel themselves getting pushed to the outside. It feels like something is pushing you. Why does our brain tell us it exists? Well, it turns out your whole orientation mechanism is called the vestibular system. And inside your head, inside your ears, are your vestibular organ. And that tells you when you are tilted or pushed or falling over. All right, so let's deal with the pushing part. It tells you when you're pushed. Inside your ears, you have hair cells that are that are indicating and sitting in fluid, and they're going to indicate your orientation. Well, when a force pushes your head in this direction, push my head that way, those hair cells get bent. On top of them are rocks, essentially. Yes, you have rocks in your head. Are little calcifications on top of these hair cells. So when we tilt our head, those rocks are heavy, and they cause those hair cells to bend. When we push our head, those rocks are pushed, and they cause our hair cells to bend, and it tells us that we're tilted, that we're being tilted outward. They're loosely connected to our skull. So now let's imagine that we are, through those hair cells, we're in this circle. And because it takes a certain force to move the hair cell of a certain mass in a circle, a certain speed at a certain radius, because those rocks are a little bit heavier, to have them going at that same speed, we need a little bigger radius. And so the force of going in the circle isn't big enough for those rocks like it is for those hair cells. And so those rocks move a little bit further out, go in a straight line until the force is big enough to pull them back into that circle. And that little bit of movement out is the bending of the hair cells. And when those hair cells bend, our brain says something's shoving me over there. So totally a misperception inside the brain. Great system for balance. Sometimes our brain gets a little confused with some of the physics. So, fun little neuroscience trivia there, but getting back to the idea that nothing is pushing us out, nothing is pushing this ball out. It's the lack of the force that is causing it to now go in what it was always doing to begin with, going in a straight line. It's no longer being caused to turn. That's what centrifugal force is all about. It's fictitious force. The force that's really happening to move that object in a circle is the centripetal or centripetal force. All right, let's do some practice and some examples on how we use this to solve problems, and then you'll be all set with Chapter 8. Good job.